Hello everybody, welcome to another mini lecture on the topic of mechanics. In this one we are going to talk about the conservation of the impulse. So let me describe our setting. We look at a system which is made up of n particles, and for now, without loss of generality, let's assume that n is equal to 3. But you can pick any n you like. So we look at such a system, which is made up of, in our case, particle 1, particle 2 and particle 3. And we imagine that these particles live in a sort of, well, isolated tank. So there are walls around these particles, so there are no external influences on this system, which is made up of particles 1, 2 and 3. But of course there is interaction between these particles. You can imagine these particles moving around in this tank, and this particle exerts a force on this particle and on this, and vice versa, this on this, and this on this, and this on this, and we have one left, this on this. And we can say a little bit about these forces by using the Aktio gleich is equal to Reaktio principle. For every force that one particle, let's say particle 1, exerts on another particle, let's say 2, there is a force that is of equal size but is in the opposite direction. So if we call this one here the force that particle 1 exerts on particle 2, F21, and this force from particle 2 to particle 1, F12, then we have the relationship that F12 is equal to minus F21. And we have a similar relationship for each pair of forces between every pair of particles. And since we want to talk about the conservation of the impulse, let me quickly remind you of the definition of the impulse. The impulse is the following. It is P, which is defined to be m, the mass of a particle you are looking at, times the velocity of this particle. And since we're now looking at a bunch of particles, we need some index here. So Pi is the impulse of the ith particle, and of course this has the mass mi and a velocity vi. And what we also will need is the time derivative of the impulse, which we denote by Pi dot, right? We could also write dp by dt. This would be the same, but I'm choosing this notation, which is quite common. So this is the time derivative, and we get this, well, simply by deriving the right-hand side, which is mi times ai, denoting the acceleration, which is of course the derivative of the velocity. So we have this, and well, we need one more definition before we can come to the conservation of the impulse. Namely, we need of course the definition of the impulse of the whole system, which we will call capital P without an index. This is the impulse of all the system, and this is simply defined as the sum P1 plus P2 plus P3, or in general it is the sum I ranges from 1 to n when you're talking about n particles of the impulses Pi. And now what does the principle of conservation of the impulse say? Well, it simply says that this P doesn't change in time, it stays the same. You look at the system at one point in time, you find a certain P, you look at an arbitrary later point in time and you find the same P. This is what we need to prove, and to prove this we will just show that the derivative of this is 0, and this will suffice. So let's get into our calculation. So the derivative of this, can you see this? I'm going to write this a little bit lower. So the derivative of P, well, this is just the sum of the derivatives of P1 plus the derivative of P2 plus the derivative of P3, so that we can write the derivative of P is this plus this plus this. And now note that we can express each of these impulses of the particles I in another form using Newton's first law, which is F is equal to ma. And now if you look here we have ma. So this change in the impulse of the particle I is nothing but Fi, which is the combined force that is exerted on the particle I. And we're going to use this to replace this expression by some F1 plus F2 plus F3. And note that these capital F's are not the same as these little f's here, but of course they are related, and precisely this relation will lead us to the conclusion of our proof. So we just need to plug in now for F this relationship between the small f's and the big f's. In other words, we need to spell out what forces are exerted on the various particles. So F1, as I have said, is the force on particle 1. So let's write this down. F1. Well, this is the force that the particle 1 exerts on itself, which is of course 0, plus the particle that the force that the particle 2 exerts on 1, plus the force exerted by 3 on 1. So this is F1 2 plus F1 3, and similarly for F2 we have F2 1 plus F2 3, and for F3 we have, this is F3 1 plus F3 2. And what this says over here is that we have to sum these three forces, F1, F2, F3. So let's erase them now and just write a plus here. Plus this. And remember, what we want to show is that this is 0, so that this time derivative of P is equal to 0. And to do this, to see that this is indeed 0, we need to remember this relationship. And we need to remember that there is such a relationship for every pair, as I have mentioned. So let's start. We have f12. This is the same as minus f21. So if you add this and this, you get 0. And similarly for f13 and f31, and for f32 and f23. So our sum is 0. And this shows that indeed the time derivative of the impulse of our whole system is 0, so the impulse stays the same. And this concludes the proof of our theorem. Thank you for watching. For more on physics and especially mechanics, have a look at my channel and see you next time.